Today, we're diving into a really clever data structure that's all about speed and long-term memory. It's called the least frequently used cache, or LFU for short. So just think about that for a second. Most caches are obsessed with what you just used. But what if you need something that keeps track of what's been popular over the long haul? Well, that's the exact problem the LFU cache is built to solve. And believe me, it does it with some serious speed. So here's how we're going to break it down. First, we'll get a clear definition of what an LFU cache actually is. Then, we'll peek behind the curtain at the brilliant data structures that make it so incredibly fast. After that, we'll walk through a step-by-step example to really see it in action. And finally, we'll wrap up by looking at where this awesome tool actually gets used out in the wild. All right, so what's the big idea here? It's really all about a shift in thinking. We're moving away from caring about when something was last used to caring about how often it's been used. It's a whole different game. Here's the rule of the road. When an LFU cache gets full and needs to make space, it looks for the item with the absolute lowest access count and boots it. It's that simple. Now, what if you have a tie? A few items with the same low count. Well, then it just falls back to a familiar strategy. It gets rid of the one that's also the least recently used out of that group. And this is the key difference when you compare it to something you might be more familiar with, the LRU, or least recently used cache. See, LRU only cares about the last time you touched an item. LFU, on the other hand, it has a much better memory. It's all about valuing the items that have proven their worth over time, not just in the last few seconds. Okay, now for the really cool part. How in the world does this thing stay so fast? The goal here is what we call constant time, or O of 1 performance. And what that means is, it doesn't matter if your cache has 100 items or 1,000,000. The time it takes to get something or add something stays the same. It just doesn't slow down. So this is the big puzzle, right? I mean, if you had to look through every single item in the cache just to find the one with the lowest count, your whole system would grind to a halt. The solution isn't brute force. It's actually a really elegant combination of data structures. To wrap our heads around this, let's use a little analogy. Picture a library. Each shelf is labeled with a frequency number, like used 1 time, used 2 times, and so on. The books on each shelf, those are our cached items. And on any given shelf, we always keep the most recently used books to the far left. This mental picture perfectly captures the data structure we're about to build. Now, to bring our library to life in code, we need 3 key things. We've got 2 hash maps and 1 super simple variable. And when you put them all together, they work in perfect harmony to give us that incredible O1 speed. First up, we've got the key to node map. Think of this as our digital card catalog. You give it the title of the book, the key, and bam, it tells you exactly where that item is. No searching, no scanning, just instant access. Next, we have the freak to list map. These are the shelves themselves. The keys are the frequencies, 1, 2, 3, and so on, and the values are the lists of all the items that have been accessed exactly that many times. It's like having a dedicated shelf for everything that's been used twice, another for 3 times, and so on. And finally, our little secret weapon, min freak. This is just a simple number. A little bookmark that always tells us the lowest frequency shelf that actually has stuff on it. So when it's time to kick something out, we don't have to go searching. MinFreak tells us exactly where to look. And what's the result of putting these 3 pieces together? You guessed it, every get, every put operation, it all happens in constant time. A quick lookup, a fast update, and you're done. The performance never degrades no matter how big the cache gets. It's just beautifully efficient. Okay, theory is great, but seeing this whole system in motion is what really makes it click. So let's just walk through a really simple example, step by step. So at the heart of everything is this little operation we can call touching an item. Every time we get or update something, we do these 5 things. We find it, we pull it off its current shelf, we update its frequency count, and then we place it at the very front of the next shelf up. And here's the clever bit. If its old shelf is now empty, we update our min freak marker so we don't lose our place. Okay, let's do this. We've got an empty cache, and it can only hold 2 items. So first we put item A with key 1. As you can see in the state column, it creates a list for frequency 1, and item 1 is in it. Our min freak tracker points to 1. Simple. Now we put item B with key 2. It's also new, so it joins the frequency 1 list. See how it's at the front? That's because it's the most recent. Our min frequency is still 1 because that's still our lowest occupied shelf. Now watch this. We do a get 1. What happens? Well, item 1 gets yanked off the frequency 1 shelf. Its count gets bumped to 2, so we create a new shelf for frequency 2 and pop item 1 right there. Now here's the important part. Look at min freak. It's still 1. Why? Because item 2 is still sitting back on that frequency 1 shelf, holding the spot. And here it is, the moment of truth. Eviction. We try to put a new item, C, but we're full. So the system looks at min freak, which is 1. It goes to that frequency 1 shelf, and it removes the least recently used item there, which is our old friend key 2. Poof, it's gone. Now there's space, so our new item, key 3, gets added to the front of that frequency 1 list. And min freak stays at 1, pointing to our newest item. So we get how it works now, but the real question is, where would you actually use this thing? Let's talk about the practical side of it, the good, the bad, and the trade-offs. LFU absolutely shines when you've got things that have a stable, long-term popularity. Think about the featured products on Amazon's homepage. If they used a simple LRU cache, a few random clicks could kick out a bestseller. LFU prevents that. Same deal for really important API endpoints or user settings that are hit over and over again. In these situations, how often something is used is a way better signal than how recently. And this table really sums up the big trade-off. LFU is your champion for stable workloads, but its big weakness, it can hang on to old stuff that used to be popular but is now totally stale. LRU is the opposite. It's great at adapting to new trends and bursts of traffic, but its weakness is that it can accidentally throw out something that's consistently popular just because it hasn't been used in the last 5 seconds. And this is the key thing to remember. A pure LFU cache has a bit of a blind spot. It can suffer from what's called cache pollution, where an item that was a huge hit last month but is totally irrelevant today is still hogging precious space just because its access count is so high. Which really leaves us with one final big question to think about. If LFU's greatest strength, its amazing memory, is also its biggest weakness, how could we fix that? How could we build a cache that's smart enough to remember what's popular, but also knows when it's time to forget? Well, that's where you get into even more advanced ideas, but that's a story for another time.